This is the final presentation of the analysis and redesign of a can opener.
As seen here, this is the production volume for the can opener. Given the growing demand for can openers and the CAGR of 5.2%, there's an estimated global annual production of 3.15 million units.
The CAD for the can opener was obtained from GrabCAD. On the left is the can opener with all its parts in the final assembled position, and on the right is the exploded view with part numbers and labels for all non-fastener parts.
Primary customers are ordinary household members who need to open up canned goods without a pull tab for various daily uses, while our secondary customers are the elderly or physically impaired that do not possess the same grip strength as most people, and our can opener will be adjusted to accommodate this. And this is our FAST diagram. It has two main functive branches relating to stabilizing the can and cutting the can, which is the main function of our can opener.
The function component mapping matrix contains all the can opener parts along with the functions that each part performs in the can opening process. For example, the upper and lower frame pivots maintain alignment and apply and maintain pressure. The upper and lower gears with their pins work to rotate the can and maintain pressure. The blade is used to pierce the can, while the upper and lower grips help to maintain alignment and add comfort.
Here, we organize the components based on cost and their functional importance. Based on this analysis, we recommend redesigning the can rotating gear wheel, lower gear, upper gear, and the can cutting blade due to their high processing costs.
We see in the function differentiation table what differs between customer segments in relation to functional requirements are the applying pressure, maintaining pressure, and rotating the can. These correspond in the component commonality table to the upper handle grip, lower handle grip, upper gear, lower gear, and the crank handle as modules.
Here's our two modules for primary and secondary consumers. The handles and crank were redesigned for easier use by the elderly and physically impaired.
We see here that the common interfaces are the upper and lower frame pivots, which allow for the insert of the grip handles, and these have variant modules. The pin holding the crank handle and the upper gear to the upper frame pivots is also a common interface, and the pin holding the lower gear to the lower handle pivot is another common interface.
This is the product family assembly diagram. In both sequences, differentiation occurs after the addition of the crank handle, with the second case being the furthest that differentiation can be delayed.
The total manual assembly time of the original design was calculated to be 70.65 seconds with an efficiency of 34%. The upper gear, spacer, blade, and upper gear pin clip subassembly was chosen for the platform component redesign due to their ability to be combined into a single part without impacting the function of the can opener and high assembly time. The blade and the upper gear were also two of the high manufacturing cost components, so combining these parts into one part could also result in a lower overall manufacturing cost. The crank handle was selected as the module component redesign because of its high assembly time and its features identified that could be redesigned to reduce the time while also lowering the manufacturing cost without impacting its function. Here is the before versus after CAD of the upper gear, spacer, blade, and upper gear pin clip subassembly with the changes called out. And here is the before versus after CAD of the crank handle with the changes called out. After these redesigns, the total assembly time decreased by 12.82 seconds. The impact from these changes on part function and manufacturing costs are also shown here. The handle clip, lower gear, and can rotating gear wheel subassembly was selected for redesign due to the small lightweight parts that are all assembled in a straight line. The total automated subassembly cost for the original design was calculated to be 3.42 cents. The parts chosen have a high functional importance to rotate the can while opening, and with automated assembly we can ensure they are installed in the correct positions. Here's the before versus after CAD of the handle clip, lower gear, and can rotating gear wheel with the changes called out. After these redesigns, the total assembly cost decreased by 1.05 cents. The impacts from the changes on part function and manufacturing costs are also shown here.
For the can rotating gear, the critical dimensions are the thickness of the gear and the diameter. This is in order to maintain alignment and pressure as according to the FCMM. Tolerance will be 0.5 millimeters for both, and the process we decided on was machining, primarily due to the material being stainless steel and the geometry of the part. For the handle clip, the critical dimensions are the height and width of the clip in order to maintain alignment as according to the FCMM. Tolerance will be 0.25 millimeters for both, as to again maintain alignment, and the process decided on was injection molding, primarily due to the material, being high-impact PET. For the can rotating gear, analytical methods resulted in a total cost per part of $8.69. DfM Pro did not result in any recommendations. However, it's important to note that the entire edge of the part, including all of the teeth, which are the most labor-intensive part to produce, were considered an unanalyzed region by the software. Therefore, we decided to still make some adjustments in order to reduce the cost of producing the part, both analytically and through estimates through hubs.
By making modifications to the teeth and center hub of the gear, we were able to achieve a 22.32% reduction to its machining cost, resulting in a value of $6.75. According to a quote from Hubs for our redesigned gear, we achieved a cost reduction of 44.47%, decreasing 58 cents to $1.43 per part.
The other component that we redesigned was the handle clip. As we see before, the cost estimate was around $0.0152 per part. And in the DfM Pro, 6 recommendations were given to improve the design for ejection molding, specifically the rip parameters, the minimum draft angle, and the uniform wall thickness. After the redesign, we see the analytical method gave a cost estimate of $0.015 per part, and the reduction was around 0.6%. Given the production volume, this dollar saved was around 320, and this had no impact on the product function as well as the assembly cost. And as seen in DfM Pro after, 3 recommendations for the changes were fixed. Specifically, if we see here, the draft angle to ease the removal of the mold, the integrated locator to add chamfer to match the lower gear locator, and avoiding the sharp corners and added fillets on all external and internal corners to reduce stress concentration.
Product service system. The design of our system will be a subscription-based service where customers can get maintenance or recycling right to their door. To improve customer experience, we'll be offering a service that helps your cut and openers last longer, thus creating a more cost-efficient customer experience. The biggest improvement being the convenience of not having to replace parts or whole units themselves. The recycling program will help in the reduction of waste, promote sustainability and usability, and reduce the overall carbon footprint, as well as save customers money by offering discounts for new products. Conclusion and design critiques. For manual assembly, we're able to decrease the total time of assembly by 12.82 seconds. For automated, we save $1.05 per assembly. For the cam rotating gear, we're able to save $1.94 per part, while for the handle clips, we're only able to reduce price by 0.6%. Some of the critiques we had were we should have done more focusing on functional analysis during earlier stages of the development, and done more research in the customer feedback of previous designs. If we were to start over, we would have implemented more iterative prototyping, leading to a more customer-centric design, and we would have focused more on sustainability.